So Chapter 21 material covers transition metals and coordination chemistry. So basically a lot of the stuff that we've done is all what we called main group chemistry, which is the S block and P block primarily. And that's what you do in most of general chemistry is that, including sort of that introduction to organic chemistry. When you do organic chemistry, that's almost entirely in the main group. But another area of chemistry is transition metal chemistry, which really falls under organometallic chemistry or inorganic chemistry. Okay. And so what we'll be doing with transition metal chemistry is looking at the transition metals first, some generic basic properties of transition metals, and then we're going to start to look at what's called coordination chemistry, which is essentially transition metals that have ligands bound to them. And we talked a little bit about ligands way back, what was that, in chapter 16 with formation reactions. And so we'll look at some of the chemical compounds that can form here as well. So starting down this path, the thing to begin with is just sort of this transition metal survey. So basically the idea here is let's just get a feel for what transition metals are. And we've talked about metals in the past. We've talked about them though as far as all the things that all metals have in common. Before we sort of get back to that and review a little bit of that, let's think about the properties of the different elements. And so when we've talked about sort of metallic properties versus non-metallic properties, right? One of the things that we've said is in the periodic table, right? As you go down the periodic table, or if you go from right to left across the periodic table, right? Or if you will, this direction, right? We're saying that we have an increase or more metallic character. Okay. And so it turns out for transition metals, it's actually not a whole lot different between transition metals. And in fact, with transition metals, there tend to be similarities within periods as well as groups, right? We know groups react the same way because that's why they're grouped the way they are. But it turns out that there tend to be a lot of similarities within the groups as well. Now, the similarities have to do with oxidation states, electron configurations, etc., that we'll start to explore as we proceed through the chapter. Now, when we think about what the uses of transition metals are, well, we find transition metals in a lot of places. So if you think about things like iron, right? Iron's pretty self-explanatory. All of the noble metals, the copper, silver, gold, right? Those are shiny metals, so they're more valuable, right? So those particular metals are things that we're really familiar with. We've seen a lot, right? But there are other compounds out there that become more and more important to us as we start to understand where they're used. For example, chromium is used in stainless steel, and there are a variety of other compounds used in stainless steel to help provide desirable redox properties to the iron. So their alloys are formed from things like iron and chromium or iron and vanadium, and a variety of other mixtures out there that have been engineered to basically do things like stop the iron from oxidizing and forming rust. Chromium is one of the common ones that's involved in the production of stainless steel. There are cobalt alloys, and cobalt is used in catalysts and batteries, so those are a common location you'd find that. Platinum and palladium are catalysts in particular. The catalyst that you'd have for with platinum and palladium, so those are really useful in things like hydrogenation catalysts, where you're adding hydrogen across a double bond. And so the properties of the individual metals will lend themselves to things in catalysis oftentimes. There's rhodium catalysts, zirconium catalysts that are used in things like making plastics and the like, but there's all kinds of catalysts out there. And the d orbitals allow for a broader range of properties of those catalysts, which allow us to make, like, say, new plastics and the like, okay? Now, just in general, when we think about properties of metals and transition metals, they're going to follow the properties of metals in general. Things like, yeah, they're shiny, right? They are both electrically and thermally conductive, right? Copper is still often used in wiring. Aluminum can be used in wiring, but copper is a better conductor than aluminum. They're ductile or malleable to some extent. And although they do have variations in how rigid they are and what their melting points are, depending upon, again, those orbitals and how those the orbitals overlap and how the orbitals are filled in the metallic bonding. But one of the interesting things that we haven't gotten into a lot is this new idea of, well, there are a lot of possible oxidation states for a variety of metals. And the oxidation state of the metal is going to have implications for what can be done with it. The other thing we haven't spent much time on, we only did really in chapter 16, is we looked at these complex ions, right? These coordination compounds. And those coordination compounds come from these cations, right? Where the cations form these complex ions. You know, complex ions have a lot of interesting properties to them. Most of them are paramagnetic. Remember, paramagnetic means they have some number of unpaired electrons. And if we're lucky, we'll get through some of the reason for this. Unfortunately, since we're so short on time, we may not get through as much as I would like to, because I think there's some really cool things there. Another thing is these coordination compounds, they do form compounds of different colors, and the colors depend on a couple of things, okay? Those colors depend on, really they're two things. What is the metal, okay? And what is or are the ligands? Okay, so the ligands and the metal will dictate what color it is, because with colored compounds, we're still talking about, just like we did back in chapter 7, where we looked at hydrogen and hydrogen spectrum, right? The transitions between energy levels, and the metal is going to have characteristic energy levels, and the shape of the molecule will help to, will be part of the energy levels of the molecule as a whole, right? So the ligands are going to have an effect on the orbitals that are surrounding that metal. So whatever ligands you have, they can cause these energy levels to be farther apart, closer together, depending upon what the ligands are. Thus, when you have electronic transitions, right? Electron goes up, relaxes back down, gives off light, etc. What color light is absorbed by the compound, those are things that are going to be governed by the metal, its oxidation state, and the ligands that are bonded to that metal. And so hopefully we'll have enough time to get to that part of it, though I'm not going to push us too fast through it. It's some really interesting things that come about this. Before we dive super deeply into the complexes themselves, just transition metals in general, when we think about their electron configurations, right? Remember, we always talk about having, if you remember, filling electron orbitals, right? We fill the 1s, then the 2s, then the 2p, then the 3s, 3d, sorry, 3s, 3p, ahead of myself, 3p, then it's the 4s, and then the 3d electrons that we tend to fill. And so once we hit period 4, right, we can think about the 4s electrons being related to the alkali and alkaline earth metals in period 4, and then after that we're filling up electrons into the 3d orbitals. Now, when it comes to the transition metals, you'll notice that we have some weird exceptions here and there to how the orbitals are filled with the electrons. And largely, these are experimentally determined. The ones that I'm really interested in you seeing and really knowing are things like the deviations or the of how we fill the orbitals. So things like chromium and molybdenum, where we would actually fill, as you can see, half fill all of the 4s and 3d orbitals and 5s and 4d orbitals for molybdenum, rather than filling the s orbitals first. Now, there are only certain ones that I really want you to know. Chromium is one, molybdenum is one. Notice the tungsten doesn't have that same process once you get down into period 6. Another one or couple to know are the noble metals, right? Copper fills the 4s half filled, and the 3d fully filled, right? Silver has the 5s half filled and the 4d fully filled, and gold. So the noble metals all do this, right? And again, these are just the valence electron configurations shown here for each of these metals. Now, the other thing of note here is when it comes to ionization, okay? So when ionizing transition metals, right? Because they're going to make cations, right? And those cations are going to form when the substance loses electrons. So when ionizing these transition metals, the transition metals are going to lose electrons from the s orbitals first. Before losing the d electrons. So if you were to make copper 1, right, copper 1 would lose its s electron, right, first, and you'd be left with 10d electrons. And so that's a key to understanding the chemistry that goes on in transition metal and complex ions, is how they ionize as well. It's just knowing that they lose those electrons first. Now, the reason that they would lose those electrons first happens to be with little subtleties in the orbitals that are filled or half filled with the electrons. Those energies can kind of shift a little bit, and that's sort of beyond the scope of this course. That's more of an inorganic course. You may cover in an undergraduate chemistry course that's an inorganic one. I think so. I took that one my senior year of college. Or you might not even see this in the subtlety of that, because it is so subtle. You may not even see it unless you were taking a specific graduate course on it. But the thing to know is that they do lose those s electrons first. Okay. And so just some little things about the first row of the transition metals. If you look at the possible oxidation states, like we have over here, right? So common oxidation states for those metals, and we can consider them of the 3D transition metals, right? Those are the ones that have 4s and 3D. When they have go to their cation form, right, they're going to lose those 4s electrons first, right? And so scandium and titanium will tend to be +3 and +4, so they're going to lose all of their valence electrons. Vanadium, you can see, has 4 different common oxidation states. Chromium 3 of them, and manganese 2 of them. And notice, especially for these the first 5 here, right? These elements lose all, or can lose up to all of their valence electrons. Whereas when you start to get into iron and cobalt and nickel and copper, they're only going to lose 1, 2, or 3. When copper, for example, loses 1 electron, it still has a full D shell. When nickel loses electrons, it only loses the s electrons. When zinc loses electrons, it loses the s electrons and still has its full D shell. And so that's going to be something that we're going to see also. Another thing is, if iron loses 2 electrons, it has a fully half-filled D shell. And if cobalt loses 3 electrons, it will have a fully half-filled D shell. And that is going to have some implications for the magnetism, right? Magnetism being related to the number of unpaired electrons. Okay. Now, if we think about some properties of the transition metals, there's a bit of trivia in this, but there are some interesting sort of bits of data here. Things like melting points, densities, where you'd find it, uses. So a lot of these things I'm just not gonna dive into too much. With iron, iron is used in a lot of well, it's as iron, or in alloys like steel, right? Steel is an alloy that incorporates carbon into it. You'll find manganese primarily in a bunch of alloys, chromium and stainless steel. Vanadium is one of those compounds, I think I mentioned that one before, in stainless steel, right? It's incorporated in stainless steel to help stop that stainless steel from rusting. Titanium. So titanium is one of those substances that is like used in things like alloys that are put into the human body, right? And so, you know, they have titanium joints, if you will, or titanium, you know, bone replacement, essentially, is where you'd find some of that stuff. Cobalt. One of the more interesting things, I think, is cobalt being used in as a coloring agent for glass and glazes. Nickel is, of course, used in coins. It's got that nice shininess to it, right? It's lustrous. It's also used, of course, in batteries, like the nickel cadmium battery, right? So NiCad batteries, if you're familiar with those. Then you have things like copper. Copper is found in a lot of places, a bunch of alloys like brass and bronze. It's found as in wires that you'd use in your home, potentially. Coins, of course, because it is one of those noble metals, and since it's shiny and it tends to be more valued than a lot. And then there's zinc. Zinc is, of course, we talked about one of the biggest uses of zinc, right, in galvanization, or as a sacrificial anode in a lot of cases. Right, and so that's a big key for zinc is it's used in, and all of these really are important when it comes to redox chemistry. Now, one of the big keys to transition metal chemistry is actually what we call the d electron count, and this d electron count is really for transition metal ions. And you'll notice if we go back up here, other than for scandium and titanium, notice all of these tend to have, and I'll just kind of box these in here, I guess, to make sure they stand out. They all tend to have these nice +2 ions, and they all kind of make these +2 ions, except, well, scandium and titanium will, but they're just not as common. Right, but those +2 ions are going to be things that we'll explore a little bit in here for the moment. Now, what happens is when the substances ionize, right, they lose, right, those two 4s electrons, right, or I could say they lose both of their 4s electrons, so I don't get any extra numbers in there. Remember, right now we're just looking at the first row of the transition metals, right? So the 3D, which is in period 4. So they lose both 4s electrons first, okay? And so for all of these ions that we have here, they're +2 ions. If you look at scandium, right, scandium 2, if you think about scandium itself, just scandium would be 4s2, 3d1, and then if it loses those electrons, you have 1 d electron remaining, and we call that d1, okay? Right, titanium would be 4s2, 3d2, but if it loses those 2s electrons, it only has 2 d electrons remaining, so we call that a d2 metal. Vanadium would be d3, chromium would be d4, manganese would be D5, iron is D6, right? Cobalt is D7. Actually, D8 is sort of one of those interesting ones. D8, nickel, and platinum and palladium are all D8 metals in their +2 ionic form, and that's going to have some implications for the shapes of those molecules that as their the transition metal or the complex ions are formed. Right? Copper, silver, and gold, if they're +2, they tend to be D9. They don't always want to be D9, right? So we know that silver generally wants to be silver plus. Gold also tends to be, that would be AU. Right? Gold would also usually tend to want to be a +1 ion because those actually prefer to keep their full D shell and only lose one electron. Zinc, though, will be D10, so it'll have a fully filled D shell. But that's a common thing here, that these elements tend to like to have that +2 ionic form as one of their more common ions, at least that you'll find in the period 4 or the first row of the transition metals. Okay, and that D electron count is something that we're going to refer back to a little bit later on once we start to know a little bit more about the ligands and the shapes of the molecules that we see, because the number of D electrons will actually have implications for the magnetism of these complex ions. And we'll start to see how that is later once we've learned about some of these ligands and what those ligands do to the orbitals or the d orbitals of the of that metal ion as those complex ions are formed. And that's sort of where we're headed now. Okay, coordination compounds. Now, largely we're going to stick with the first row of the transition metal, so period 4, which has the 3 D electrons are the electrons that remain in those transition metals. And there are a couple things that we need to know. The first thing that we need to know is what's called the coordination number. Okay, the coordination number is here, as you can see, the number of bonds between the transition metal and ligands. Okay, so what we need to know, and this is kind of the key, it's the number of bonds. Okay, this is similar to the steric number that we did back in VSEPR theory, but it's not exactly the same thing. The key here is that it's the number of bonds. So when you have the transition metal ion, that'll be in the center, and then you'll have ligands that are bonded to it. Okay, we'll talk about the ligand metal bonding in a little bit. But it's basically the coordination of number is the number of, another way to look at this, the number of atoms that are bonded to that metal ligand. Okay, they'll generally have 2 to 8. The most common you'll see are 6 or 4. And when we can think about these metal ions and the transition metal compounds, these complex ions, we're not going to be worried about lone pairs on that central atom because of how they fill the d orbitals. And I'm going to be a little hand wavy on this for the moment. But what we'll see is the number of bonded atoms is going to be similar to the steric number. So the coordination number is similar to that steric number in a sense. Now, the most common geometries that we'll see are going to be 2, 4, and 6, and in particular, 4 or 6. Now, what we'll find is most of the transition metals are going to be form octahedral complexes. Okay, occasionally you'll have some square planar ones and some tetrahedral ones. The tetrahedral ones tend to come from D10 ions, and the square planar ones tend to come from D8 ions. And so a way to think about that is when it comes to a ligand metal bond, which if you remember, a ligand is a Lewis base, so it's an electron pair donor. That Lewis base has to have a lone pair of electrons in an orbital, and the metal has to have a lone, or has to have an empty orbital. And so to get something tetrahedral, we know back from way back in, well, we actually, what he just did in organic chemistry, but also from what we did back in Chem 101 and VSEPR theory and, chapters 8 and 9, is that if you have something tetrahedral, it would be sp3 hybridized. So if you have a D10 metal, for example, zinc, right? So zinc would be a D10 metal. So that would have, if you remember, it would have the 4s and the 3 of those 4p orbitals, so 4px, 4py, and 4pz, which are all unfilled, right? And so if they're unfilled and those electrons are donated by the bonded atoms, what you're going to wind up getting is an sp3 hybridized zinc atom or zinc ion as the central atom of a tetrahedral complex. Now, ligands, okay, a key here, ligands, they're Lewis bases that form these covalent bonds, right? So when we say it's a Lewis base, right, it's a lone pair donor or an electron pair donor, if you prefer, either way. Okay, and it forms, remember, these coordinate covalent bonds. Okay, when we say a coordinate covalent bond, we still have orbital overlap. Okay, where those overlap, you have both electrons are donated by a ligand. And so if you were thinking about, say, the hydrogen bonded to a carbon, right? The hydrogen has an electron, the carbon has an electron, you get the overlap of the orbitals, they're both putting an electron in, and that gives you a covalent bond. The difference is, now you have a ligand that has a lone pair of electrons and you get the overlap of the orbitals, but the ligand gives both of the electrons to the orbitals to share. And those then are shared by the transition metal and that ligand atom, the atom that's bound from the ligand to the central atom. And so just as a reminder, right, some of the shapes that you'll see in some of these transition metal ions, things like iron, nickel. So nickel is an interesting one. Nickel can, as a D8 molecule, nickel 2+, it can form something that's octahedral, but nickel actually tends to want to be square planar. And there's a reason for that that we'll get to eventually, but that's an example of a compound that would be square planar. Cobalt, okay, so cobalt, if we go back up to our periodic table, just to, here we go, cobalt here, right, is D7, okay, so this is going to be, this is one of the other versions of a 2+ ion that forms something tetrahedral. Generally, zinc is kind of the best example, with also cadmium being in that same category. Silver forms this a complex ion that has 2 ammonia molecules bonded to it, and that'll form a complex that is linear. So these are all possible ways of having complex ions in their geometries, but again, the most common are going to be, right, these octahedral complexes, okay, and the either tetrahedral or square planar. Those are the most common that we're going to see. Now, when it comes to the ligands and forming the bond with the metal, the next thing to look at is what are these ligands, okay? So the ligands that we have interest in, and we've got a sort of categories to look at. And among these categories are, so for the types of ligand, we consider ligands based on the number of bonds that they form with a metal, okay? And so the term we use is dentate, okay? So dentate says how many places does it bind, right? Dentate as in teeth, like how many places does it bite onto that metal, if you will, right? And so that's where the term actually comes from, is saying, oh, this bites onto the metal at this point, right? And so a unidentate ligand would only form one bond with the metal, right? Uni and one. So these are all the Greek prefixes rather than the Latin prefixes for this. And so things like water, right? So your Lewis structure will give you some understanding of, I'll just draw the Lewis structure in here, will give you some understanding of how these molecules might bind. So if you have water, we'll draw in our lone pairs of electrons. Right, so you have these lone pairs of electrons. A lone pair can form a bond with a given transition metal, right? And so you can donate a lone pair through this lone, or through one of those two lone pairs of the water molecule. If you look at Cn minus, it has a structure like this. Okay, where the formal charge on the carbon is -1. And so this particular substance can, right, this cyanide can bind through either the carbon or the nitrogen. Ammonia is another example. Right, ammonia has this lone pair of electrons, so it'll bind to the bond will form between the nitrogen and the metal ion. A nitro, or so NO2 minus, can bind through either an oxygen or through the nitrogen. You've got thiocyanate. And the thiocyanate can bind through either the sulfur or the nitrogen. And so with thiocyanate, you can think about the structure in one of two ways. With the formal charge of -1 either on the sulfur or on the nitrogen, and depending upon what it's bonded to, it may take preferentially one of those forms. The hydroxide ion at okay, or the halogens, right? So chlorine would be X, right? So X is equal to a halogen. And that's something you'll commonly see with halogens. They tend to be labeled as X's. Or halides, I should say, not just halogens. Okay, so those are all examples. Notice they all have lone pairs of electrons that could form bonds when you have the overlap of one of the orbitals from that ligand with an orbital coming from the central metal ion. And these ligands will donate both electrons to form that bond. But we also have bidentate ligands. So bidentate ligands can form two bonds. And so things like oxalate, so the oxalate molecule, or ion, I should say. All right, so the oxalate polyatomic ion so I want you to see how all of these Lewis structures would work. All right, so each of the singly bonded oxygens has a negative charged or negative formal charge to it. And so you can look at, like, where's it going to bind? Well, based on electron density, probably to the more negative side of it. This other thing here, so ethylene diamine, okay, is a bidentate ligand. I'll draw the Lewis structure, and then there's some abbreviations to use with ethylene diamine and then the next couple, okay? So ethylene diamine is an interesting one. It's actually a pretty cool ligand. It does bind in 2 locations. So ethylene diamine. So the diamine tells you there are 2 nitrogens. Okay, so there's one nitrogen, there's the other. The ethylene tells you have a CH2 bonded to a CH2, and those 2 nitrogens are linked via this ethylene, to an ethyl that has a nitrogen bonded to either side. The nitrogens each have another hydrogen on them and a lone pair. So when it comes to forming a bond with a metal, right, the lone pairs of electrons can be donated through either of those 2 nitrogens. That's how you get an ethylene diamine. Now this is often abbreviated in a structure as this. Okay. It's just done that way because it's just easier to, right, to sort of see the structure without having to draw all of the peripheral hydrogens or draw the carbon chain linker between the 2 nitrogens. And so that's something that you'll often see is nitrogens that are connected via just a little curved line. That's just saying that's the ethylene link in the middle, right? Right, so that's your ethylene. Okay. And so that's one of the really common ones out there that forms 2 bonds, and that'll be something we'll explore a little bit later when we look at chirality of transition metals. Diene, okay, so diene is diethylene diamine. And so this is a tridentate ligand. And so this structure bonded to another nitrogen, bonded to another one. And so you see I can play with my line angle drawings here to some extent also. And you know, a lot of the times you'll notice using sort of hybrid, if you will, from the types of structures, of drawings of structures. So you can really illustrate the important part of this, right? So this is diethylene diamine, and in the diethylene diamine, you have 3 nitrogen atoms that can form bonds to a metal ion. And we'll potentially explore some of these further, but basically since you have each of these 3 lone pairs of electrons can form a bond. And so again, this one can be abbreviated in a similar way to ethylene diamine, just to make it easier to draw those. Right? So that's diethylene diamine. Now, there are going to be some special rules for nomenclature because this can be a little bit confusing occasionally. The other one is triene, which would be triethylene diamine. Okay, and so that one will have a structure more like this. This is sort of a more rare ligand. It's not necessarily used as much. But this one can bind in 4 spots. And this one can do some interesting things. There are some other compounds that can form 4 bonds, and things like porphyrin. Okay, and I'll do that on the next page. Compounds called salin. There's just a handful of other tetradentate ligands. A lot of times, so that if you will, the triethylene diamine is interesting because it's all these single bonds, whereas a lot of the ligands, so another one would be called ACAC or acetyl acetonate. Okay, they tend to have these conjugated double bonds that lock in the atoms of the ligand into a square planar orientation. And I'll draw a porphyrin molecule or porphyrin ion in a second on the next page where I have a little bit more space. Actually, I'm going to do the same thing with EDTA. So EDTA, and all of these are actually considered to be what are called chelating ligands. Okay, a chelating ligand just binds in more than one place. EDTA is sort of that the most common of the chelating ligands. It actually tends to hold, I believe it's calcium within its 6 points of forming bonds with the metal ion. And so what it does, it's just kind of, if you have a metal ion here, right, this ligand will go and grab onto it. And a chelating ligand will tend to bind up that metal ion so it can't bond with anything else. And so it's used in a lot of places as a titrant. If in the case of studies where one wants to see, say, the concentration of a metal ion in a solution, if you add this EDTA to it and follow the spectroscopy, looking at the absorption spectroscopy, for example, as the ligand binds, it changes the absorption properties of the ion, and you can see when that ion is entirely bound up, basically. And so an EDTA titration of a sample is useful for things like biological samples, maybe water samples that are out there, but usually in aqueous media. And so we'll draw out EDTA and a porphyrin molecule here on this next page. So we'll start out with EDTA. About uppercase, there we go, ETA. So ethylene diamine tetraacetate or tetraacetic acid. Right, so that's the fully protonated version of EDTA is ethylene diamine tetraacetic acid. The ligand, as a ligand, it's ethylene diamine tetraacetate. And so that would have a structure that looks something like this. I have nitrogen. Oops, try this. That looks terrible. You got a nitrogen here in the middle. This is your ethylene diamine, right? So that should be familiar here. Each of these nitrogens will have a lone pair of electrons on them. Right? Those are 2 of the points where this particular molecule can bind. The other parts are the tetraacetates. So there's a CH2, C double bond O, bonded to O minus. So this is one of the acetates. Another one is coming off of the other side. Oop, I'm actually gonna try doing that a little bit more neatly. There we go. So there's one. Of course, if it's the acetic acid version of this, each of these acetate motifs is going to be protonated, right? You've got a tetracarboxylic acid here. There's the third of the 4 tetraacetates. Okay, and there's the 4th. And so EDTA as a chelating ligand, right, that would have a 4- charge to it once it's entirely deprotonated. And it does tend to be easier to deprotonate if you've got a metal that'll bind in there. But that can have essentially 4 locations, right? The nitrogens can all bond, and each of these acetates can bond to that ligand, such that this thing will kind of wrap around that ion and encapsulate it and hold on for dear life. So something that's interesting about these ions is the more places that these ions bind to the ligand, the stronger that ligand tends to bind. Okay, so if you have one bond that's formed, yeah, that ligand is going to be held on, right? But you can always break a bond, right? You put a little energy in, the bond can break. But if you have now 2 places where that ligand binds, right? If it binds in 2 places, well, if one of the bonds breaks, it's still in local proximity to that ion, and so it can reform that bond fairly easily just because it's very close. You'd have to break both of those binding locations in order for that ligand to come off entirely if it's a bidentate. If it's tridentate, you can say 3 times, right? In terms of a hexadentate ligand, I don't even have enough fingers on my hand to illustrate the binding of something like EDTA to a metal ion. So that EDTA really holds on to that metal ion very, very strongly. And then the other type of ligand that we'll look at today is actually one that's really a common one, and it's really good that you know, is a porphyrin. Now, a porphyrin molecule is found in places like hemoglobin, okay, and chlorophyll, right? This particular type of ligand it's found in a lot of other biological systems as well. And this is a fun one. It's been a while since I've drawn it. It's been since it's really last year, probably, when I gave the same lecture. But this one is a tetradentate ligand. It has 20 carbons. And so there is only one way to draw it, and that's with a line angle drawing. And it's a very conjugated system. Okay, so that's the basic structure of it. And then I got to put in all of these double bonds. Okay, so those 2 will just have lone pairs. These will have a lone pair with a minus charge to it. 1, 2, yeah. There we go. So this tends to be a -2 ligand. And the thing about this is you tend to have R groups or hydrocarbons of some kind that come off of here. And when that adds functionality to it, but they can come off of different locations, right? You say R prime, R double prime. In chlorophyll, for example, you have things like ethyl or methyl substituents coming off of this ring around this whole ring, okay? And so that's the idea of a porphyrin molecule. What happens is you get a metal that binds right in the middle. And this whole molecule, right, is a planar molecule, okay? When it forms a complex ion with a metal, right, it forms a mostly planar substance, or it stays, we should say, mostly planar. When it forms a complex ion. And I say it stays mostly planar because, well, this planar molecule, this has this little pocket in the middle, and depending upon how big that metal ion is, it can cause a deformation, almost like a puckering of this, this molecule, so that it kind of opens up and it forces itself to allow that metal ion in there. But that metal ion would essentially sit right here, right? You'd have that metal ion that would sit right in the middle there. And that's the idea for hemoglobin. You have an iron ion that sits right in the middle of that pocket in hemoglobin, and that's what allows oxygen to bond to it. And the oxygen will bond to that iron atom, excuse me, the iron ion in the middle of this porphyrin ligand and be transported around the body. And, you know, when it gets to a place where it needs it for a certain reaction, right, it'll be, it'll detach, although it does detach in the blood, but there's more to the equilibrium chemistry of the binding of oxygen in the blood. But the idea is that oxygen will bind to it. But also it turns out that these ligands will bind with different strengths. And so if you think about two ligands that might bind to something like the iron and hemoglobin, well, oxygen is one atom. If you think about an oxygen Lewis structure, right? So a Lewis structure for oxygen, and this isn't exactly how oxygen exists, which we talked about back in, way back in chapter 9, but you can think, okay, well, this is a ligand. It has lone pairs of electrons that could form a bond, but another molecule that's out there that could form a bond with the metal ion like iron is something like carbon monoxide. So there's another ligand that's out there, and this one has a -1 formal charge on the carbon and a +1 formal charge on the oxygen. This will bond more strongly with the oxygen. So understanding not, so ligands from the standpoint of not just how many atoms will bind to the metal, but some ligands have stronger bonds for other reasons, even though they're only going to be mono or unidentate ligands, is an important aspect of this also. And we know, just sort of, you should know based on well, at least our understanding of something like carbon monoxide poisoning, to tell which ligand is going to bond more strongly to the iron. And it turns out carbon monoxide binds more strongly to the iron in a porphyrin or a heme. So hemoglobin, heme means iron in a porphyrin with a porphyrin ligand. And so the carbon monoxide binds more strongly to the heme than oxygen does, which is why carbon monoxide poisoning is such a problem, because that carbon monoxide will stick more strongly and doesn't let an oxygen atom come in and bond to the iron to be transported around the body. And so it just, if you will, it binds up that the hemoglobin so that it can no longer transport the requisite amount of oxygen. And so this transition metal chemistry is extremely important even for us, like in our everyday life, because if we don't have it working in our body, we will cease to exist. Okay, so when it comes to nomenclature, okay, we're going to start in on some nomenclature today, and we'll go through some rules, and we'll stop before we get too far into it, because you know, as you know, nomenclature can take up a lot of space in one's head. So I'm going to go through the rules. We'll talk about the rules a little bit, and then we'll do some examples next time around. I don't think I want to get into the examples just yet. I want us to study for the exam that you're having on Thursday, but I want these rules to be there so that when we come back on Tuesday after the exam, we can just jump right into nomenclature and hopefully get through a bit of that and start to really look at the structure of these complex ions a little bit more. So a little bit of nomenclature. Okay, there are going to be some similarities to things that you've done in the past, right? For example, we're always going to name the cation first, okay? Sometimes that cation is a complex ion, and so we're going to name the whole complex ion as that cation if the complex ion is a cation, right? Then we're going to name the anion. So if the complex ion is a cation, we'll have some slightly different rules than if the complex ion is an anion, okay? Now when we name a complex ion, Yeah, so that's sort of the next part, is rules for naming a complex ion, and in particular, the ligands in the complex ion. If you have an anion ligand, okay, so an anion ligand is going to have O added to the root. So things like chloride as a ligand, right, that's Cl minus, right, that we know is one of our halides, right, halogen ions, right, that will be chloro. So in that case, it's kind of similar to what we did in the organic chemistry, right? And so if it's, again, if it's an anion, right, it'll have the ending O. For a neutral ligand, we're going to use the full name. Now, some ligands like ethylene diamine will use that full name. If we have water, though, there are some exceptions where we use common names. So water's aqua. Ammonia, that's specifically ammonia, is amine. When you have a primary amine, something like methylamine, right, we're going to use that name, methylamine. Or if it's isopropylamine, that would be the name of the ligand. CO, hey, this should be familiar, right? CO, we're going to call carbonyl. Okay, so the same way, it's a little bit of a different structure than this, because now our CO, remember, is going to be, when we think about a CO here, right, I'll go on this other side, it's not a carbonyl that's the same structure as in an organic substance, because a carbonyl in an inorganic substance, come on, triple bond, right, is going to have this structure. And that carbonyl can bind through either side. Generally, it binds through the carbon atom, though. And then if you have an NO, okay, an NO is a nitrosyl, okay? And so those are the ones that have, so we're going to use the full name of the ligand for anything other than if it's an anion, or if we have these neutral ligands, we'll use the full name unless it's one of those select few. We'll still use di, tri, tetra, penta, hexa for when we have more than one ligand. So for example, if you have 6 water molecules that are bonded to that central atom, it would be hexa aqua, okay? Or if it's 5 amines, it would be pentaamine, okay? Except there are some ligands, right? Some ligands, and this is sort of the unless here, right? Unless the ligand has a di, tri, tetra, etc. in it, right? In that case, something like ethylene diamine, right? Ethylene diamine, right, has a di in it already. And so in order to really sort of take charge and be able to explain the structure of this molecule, we're going to have to change the prefix. Instead of ethylene diamine, which would just be kind of confusing, it's actually going to be bis ethylene diamine, to have 2 ethylene diamines on something. So it'd be bis ethylene diamine. Okay. And then of course we're going to name our ligands alphabetically. So we don't use, and then we don't use the prefixes to determine order, right? So similar to how we would name the various substituents on an organic molecule, we're going to name the ligands on a complex ion alphabetically as well. Generally, we are going to use the standard way, the new version of naming metals is we're going to use label the oxidation state of the metal using that Roman numeral. So if you remember type 2 metal ions, these are basically our type 2 metal ions. And so we're going to use the Roman numeral to label the charge or the oxidation state of that metal ion. The other thing is, though, if the complex ion is an anion, right, that's a big key. That's a little different. Most of the complex ions, because they are cations already, will tend to be cations. But if the complex ion is an anion, for example, you have, say, a potassium ion is the cation, you'd be potassium, and then you would name the anion. The anion in that case could be a complex ion. in that case, you're going to use the suffix ate, right, to the root of the metal, okay? To the ate to the root of the metal. So if you will, if let's say cobalt is the metal, right, that would change to cobalt-ate, right? Or if it's, let's say iron, okay, right, which is ferrum, right? It would be ferrate. So we're going to use those Latin roots when we're naming those ions. And so this is a lot to take in, and we'll get some practice naming these, both naming complex ions from a structure and taking a structure and determining the name of the complex ion. We'll get some practice doing both of those. But again, we're going to end a little bit early here so that I don't get too far down this road, because I figure you guys have enough to deal with going into our exam on Thursday. And really, this stuff is going to be really useful going, you know, if you go forward and do some interesting things with it. There's going to be some fun things in this chapter where you're going to get to apply a lot of stuff, but I don't want to fill your heads too much, because I think the organic chemistry and the electrochemistry and the thermochemistry are all a bit more important than getting through this, unless you're going to be specifically a chemist, in which case you're going to see this stuff later in an inorganic chemistry course anyway, okay? And so with that, we'll end our lecture for the day. And you can, you know, get your studying going for the exam. Remember, tomorrow we have a review session.